I will use this clip to demonstrate how we can use the definition of a derivative to calculate the derivative of a function. Now that doesn't sound overly exciting, but we will later never use this definition to actually calculate derivatives because we have nice rules, so it is quite instructive to convince ourselves that these rules actually deliver what we know to be true about the derivative. So here we have a function f of x, and at some point x, that function will take a particular value, and here's our tangent to the function at that point. The derivative itself, this tangent, is defined as the limit of f of x plus h minus f of x divided by h as that term h goes towards 0, as it becomes smaller and smaller. And you would have seen how we can go from a chord to a tangent by reducing the delta x. So here's an example. We'll look at this particular function now. F of x is equal to x cubed, and see how we gonna use this definition of the derivative to actually calculate the first derivative of a function. So here's f of x is x cubed. In our definition of the derivative, we have this term here, f of x plus h minus f of x divided by h. So this term here. This we now want to calculate, and for that we need to calculate the term f of x plus h. But we also need minus f of x at the end, and that will be minus x cubed. Well, we know that already, and at the end we will divide by h. So all we are left with is this term f of x plus h. So let's see what it is. So instead of x cubed, we have x plus h cubed, and if you then calculate this out, you get this term. You can try that yourself, but I'll take a shortcut and just copy that solution in here, but that's just some basic algebra to establish that. You can see that already a few terms cancel out here. We have an x cubed at the beginning and a negative x cubed at the end of the numerator term, so these two terms cancel out. So we are left with a slightly simpler term, and if you see that each term in the numerator now has an h, we can easily see how the h in the denominator cancels out some terms in the numerator. So we are left with 3x squared plus 3x times h plus h squared. Now we merely need to take the limit of this term as h goes to 0. So let's write that limit as h goes to 0 of 3x squared plus 3xh plus h squared. Now we need to consider what happens if this h goes to 0. Well, both these last two terms will go to 0 themselves, which means that in the limit this term will be 3x squared. So this is the first derivative of our function f of x. So f prime x is 3x squared. This is of course again a function of x. The slope to our original function will change depending on the value of x we are looking at. If, for instance, we are looking at the value of x equals 2, then the slope is 12. And with that information we can calculate the equation which represents the tangent at a particular point. So here, down here, this is the equation we know to be the equation for the tangent. We take that f of x1, which is equal to 8, f of 2 is 8 to the right hand side, and then the first derivative at x1 equals 2 is 12, and we have x minus x1, the x1 being 2, and if we collect some terms, what we get here is negative 16 plus 12x. So that is the equation for the tangent at x1 equals 2. Okay. Okay, so it's the equation for a tangent at a particular point. We have just chosen x equals 2. We could have chosen any other x, but then the calculations would have been slightly different. So let's put in the tangent at that point. So it has this slope and it crosses the vertical axis at negative 16. So the equation here is y equals negative 16 plus 12 times x. 12, that is the slope of our original function, the red one here, at x1 equals 2, and here's the intercept. So we use the definition of a derivative to calculate that first derivative, and then we calculate the equation at a particular, for the tangent at a particular point. Here's another example, and really you should pause the clip and see whether we can replicate that calculation for this new function. Yes, pause it. Welcome back. Let's see whether you got it right. So the first thing we're gonna do is calculate f of x plus h. We've just substituted x plus h in our original function, and in the first step I just rearrange inside this parenthesis. So now I have x minus 4 plus h, and the reason I do it is because it's nicer to isolate the h. So I'm now dealing basically with two terms here, the x minus 4 and the h. These are two summands, and the sum of those two is taken to the square. You know how to calculate the square, so we got all of these terms, and at the end we have plus 32. Now we will just bring the negative 4 into the parenthesis, so we have negative 4 times x minus 4 squared minus 8 times x minus 4h plus negative 4h squared plus the 32 at the end. So this is what fx plus h is. Okay, so we have one part of our ratio here. What we now also need is the other function call minus f of x. Now f of x is just up here, that's our function, and that is pretty straightforward. It's just negative 4 times x minus 4 squared plus 32. So first I'll replicate what we calculated to be f of x plus h. This is this longish term here, that's just replicating what we calculated above. So it's basically this green, let me just highlight this in green. This is the green function f of x plus h, and now we subtract f of x, so minus, and now f of x. This will need to come into that space here. So we can see what f of x is, negative 4 x minus 4 squared plus 32. Since it starts with a negative, that negative down here will turn into a positive, so we have 4 times x minus 4 squared and then negative 32. And we divide the whole thing by h. Again, things cancel out, 32 plus and minus, then we have a 4 times x minus 4 squared, 1 plus 1 minus, so these cancel each other out. And as if by magic, this term has become much simpler. So we are left with negative 8 x minus 4h minus 4h squared over h. Again, h appears in both terms in the numerator. So what we are left with is negative 8 times x minus 4 minus 4h. So this means we've calculated this entire ratio. What we are left with now is that we need to take that ratio and see how it behaves as we take h to 0. We take the limit as h goes to 0, and let me just copy that here of negative 8 x minus 4 minus 4h. Now there's only one h here. What happens to that term in the end? If h goes to 0, it will turn 0 itself. So we are left with negative 8 times x minus 4. So this is now our derivative f prime of x is negative 8 times x minus 4. Let me replicate our original function again. That was negative 4 times x minus 4 squared. X minus 4 squared plus 32. Now, if I'd asked you to calculate the derivative of this, I would have expected you to immediately get the right result. F prime of x is equal to negative 8 times x minus 4. You would have used the power rule of derivation, and that's great. And I told you before that what we're doing in this clip, in practice you will never do. This was really only to convince you that applying this definition of the derivative leads to the same result as applying our simple rules. And we usually get this result without ever having to calculate f of x plus h and then take something to the limit. Few indeed.